going to look at pendulum motion. It's an instance of simple harmonic motion, but we'll generalize in a few minutes. Talk about that. An ideal pendulum okay. I'm going to say that's a point mass at the end of a negligible thread. That's the ideal. Okay? Now, point mass, unless you got a black hole there or something, doesn't have any mass. Okay? So, really, I say point mass. We're going to modify that slightly to say a point-like mass. And that would be a uniform sphere, okay? And that, for these purposes, acts like a point. And the only forces are the gravitational force are gravitational and tension forces. So what you have is you have this mass and gravitational forces are pulling it downward. Okay? So I'm going to call this gravitational force F sub GRAV for gravitation. Okay? And presumably it's acting straight down. It's actually acting toward the center of the Earth. That's what we perceive to be straight down from wherever we are. Okay? And then you have the force of tension on this mass. Okay? So you have the force of tension. Okay? Only those two forces. Now you've measured forces using a rubber band. You've measured gravitational forces on a rubber band, on stacks of dominoes. Okay? And you find that the force there, if you graph that force, okay. You have rubber band tension, and you have its length. Okay? Now there's some length, some maximum length that'll have no tension, or at least negligible tension. So, you know, the rubber band started out at some length. Well, you didn't measure that length, but what you measured was then the tension with various numbers of dominoes, okay? So you have discrete approximation, and usually the graph will kind of look like this. The rubber band stretches out, it gets thinner, it exerts a little less force, but then you approach the length where it starts to get stuck, tenses, before it breaks, then the tension will increase a little bit. Now, what you measured in lab is probably in this region. Probably have a slight downward concavity if you make a graph, which I'll ask you to do for Monday. I decided to give you Labor Day off because y'all did so well in your assignment that you handed Friday. Okay? Okay, so you probably here, but maybe you got to here, depending on what system you measure. The point, though, is that it's not a perfect straight line, but I can draw a straight line, if I'm lucky, if I can aim the thing correctly, that does a pretty good job of modeling that behavior. Okay? So the rubber band doesn't really give you a straight line graph, but it's pretty close as long as you don't stretch it past that 30% limit that I talked about. Okay, when you start changing the rubber band and actually permanently deforming some of those polymer chains. And I act like I know what I'm talking about. I don't know anything about polymer chains, except they slide past each other and kind of link. Never had the time or the opportunity to, I've got the opportunity, I can look it up. Never has had time to do this. This point here is not actually a data point. This is a point that you extrapolate as the 0 point for the tension. So do we understand that? Since you had your hands on the system, that should be pretty easy to understand. Okay? Lots of other things behave like this, where the tension is an approximately linear function of length. Now there's a lot more I can say about tension and so forth, but I wanted to mention this so you've got a good picture when you look at a pendulum of where this tension force comes from. You're actually stretching that string a little bit, okay? Not much. That string doesn't want to stretch much. If you stretch that thing even 1%, I believe you'd probably break it. I haven't tested that. We can test that in lab. How far can you stretch a thread before it breaks? Take a long piece of thread so we can measure the stretch. Keep pulling until it breaks. Okay? Okay, so back to the pendulum. We have these two forces. Now, imagine that these forces were exerted by rubber bands. They aren't, but they could be. You could simulate this. Okay? So you pull this rubber band here out to where it exerts this tension, and you pull the rubber band out in this direction where it exerts in that tension, right? What's going to happen?
Oh, it's going to move.
It's going to tend to move it that way, right? Just intuitively. If you don't believe me, there are rubber bands laying around. Grab a couple and try it. Pretty obvious. If you got a string that's curved like this and pull the ends, it straightens out. Okay? That's an important phenomenon. You can also use that to understand the forces exerted by an incline on an object and find that the force has to be perpendicular to the incline. I'd do that right now because there's a meter stick and there's some dominoes, but I want to talk about this. We'll come back to that. We'll do that. Okay? So the result of these two tensions is a force in this direction. It's actually kind of in this direction because obviously if the string isn't particularly elastic, you're going to swing around in an arc, and the low point of the arc is going to be here, which is related to what Tyler said earlier. On the moon, gravity tends to pull down with less, tends to lower the thing more slowly because the pendulum actually is lowering. And the direction of motion is perpendicular or tangent to the circle, to the circular arc through which it moves, which means it's perpendicular to the spring. You understand it? Make sense? Okay? So, we can draw what's called a free body diagram. I'll say a lot more about free body diagrams later, but here's a diagram. Here's our tension, that's our gravitational force, and here's our tension. Okay? And we can impose a set of coordinate axes in this. There are two alternative sets of coordinate axes that make sense for this. So this is an important point. So I'm going to draw it again. Okay, now the set of coordinate axes that I'm going to use here has the x-axis horizontal, the y-axis vertical. However, until we analyze it, we don't know what's going to be simpler. This is one candidate for the best set of coordinate axes. Another candidate, there's no reason to assume that the best set of coordinate axes will have an axis parallel to the gravitational force. We could also assume that the coordinate axes have an axis parallel to the tension force. Just because you're used to seeing the x-axis horizontal and the y-axis vertical doesn't mean that that's the best system in which to analyze whatever it is you're looking at. Okay? So we would actually stop and think about whether we want to set the coordinate axes this way or this way. And if we can't come to a conclusion, maybe we analyze it both ways. Okay? Turns out this is a better way here. But if we were analyzing the motion of an object going down an incline, we would want to have the coordinate axes like this with the x-axis parallel to the incline. And you'll see why fairly soon when we analyze this. Okay? Now, we can see that if the pendulum isn't too far from the equilibrium position, the straight down position, that well, let me talk about components. Okay. This force has a vertical component and a horizontal component. Okay? So that arrow is a vector. Hopefully you've seen vectors. We'll take a little time and talk about them a little bit. But they're fairly straightforward if you've had a decent second semester of pre-calculus or a trig course. Okay? They're really easy. And if you haven't, as long as you've had that, you can get it. Okay, so, okay, big point here. I haven't proven this. I'm only asserting it, but believe it because it's true. Okay? And we'll justify it later. This tension is completely equivalent to this force and this force. Okay? There's a little bit of it in this direction and much more of it in this direction. Okay? So we'll call this the x component of the tension, the y component of the tension. Okay? Now, since the pendulum is not accelerating significantly in the downward direction, although it is a little bit, so this is only an approximation. But since the pendulum is not accelerating in this direction, it's mostly moving in this direction, and this all depends on this distance here being small compared to this, okay? And to the extent this is small compared to this, that's true. It follows that this has to be equal and opposite to this. Because if you had a net force in this direction, you would have an acceleration in this direction. Now you do have a little bit of acceleration in this direction. But it's so small we're going to ignore it. And with that, we can see that this force has to be equal and opposite to this force. Okay? This and this are equal and opposite. Believe me? Make halfway make sense? Okay? Also, if this angle here between here and here is very small, the length of this vector and the length of this vector will be nearly equal. So I can say that these are messed up that y, didn't I? Nearly equal this and this. Okay? Well, that then follows that the length of this vector is nearly equal to the length of this vector. Okay? And also then, we can sketch a triangle over here. Okay, we can sketch this triangle. Okay? And this triangle is geometrically similar to this triangle. In other words, this side corresponds to this side to this side. Now this is a similarity, not a congruence. This is notation you should be familiar with, even though there's been a tremendous effort in the last 30 years to dumb the curriculum down so that nobody knows any geometry.
It's been largely successful.
Yeah, it has. Just wait till we get to optics, nobody understands triangles. But we should understand similar triangles well enough to understand this similarity. Okay? In other words, the sides of this are in the same proportion to one another as the sides of this. Okay? So whatever the ratio of this is to this is in the same relationship, or in the same ratio to this. Okay? So by geometric similarity, this ratio is the same as this ratio, where this distance here is x, and this is the length of the hypotenuse. Okay? Now, we have this. And F grav over L, length of this thing doesn't change. The force exerted on the mass of the pendulum by gravity doesn't change. So these two don't change. This means that Ftx is just some multiple of x. And that multiple doesn't change. It's a constant multiple of x. The other thing is, if x is negative, okay, if x is to the negative side of equilibrium, the force is to the positive side, right? So the force is opposite in direction to your displacement. Now, if x is regarded as a displacement and not a distance has no sign, a displacement can be positive or negative, it follows that you have a negative sign in front of you. Okay?
Wait, how is x negative?
Well, if x equals 0 here, so that we go ahead and put a set of coordinate axes. Okay, so here's your x direction, and here's your origin. So x is clearly negative here. X is the coordinate of this point. Okay? I labeled it kind of like the length of a side of a triangle and sort of glossed over that, but in a way that's kind of obvious if you think about it. Okay? So our conclusion is that the force of tension, which is the net force, and you know what I'm going to do? You know, remember that we made some approximations here that this is the same length as this because the angle is small? Okay? So these are all approximations. So I'm going to put a little curvy tilde over the, I'll tilde as a curvy, so I was redundant, over the equal sign to say it's an approximation. But it's an excellent approximation as long as you're not moving too far from equilibrium compared to the length of the pendulum. Keep it within 20 degrees and you're going to be hard pressed to measure any difference between ideal behavior and real behavior. Okay? Air resistance will have more effect on your results than the approximations here. Okay, so anyhow, F net is approximately equal to this, which is in turn approximately equal to negative kx, where k is just some constant. You don't have to even measure F grav or L, you can measure k directly. All you have to do is hang a pendulum and then see how much force it takes to pull it back this distance or this distance or this distance. Make a graph and look at the slope. That's going to be k. Okay? So I'm going to simplify this by calling this k something we can measure directly. But that k will be gravitational force over L. all right? Now, I haven't done the trig of this, but the argument actually pretty much holds. You have to kind of prove that the small displacement or the small angle approximations work. So if you want to get really rigorous about it, you can do the trig, and we will, but not right now. We want to get a conceptual idea that's actually a pretty rigorous argument, not just conceptual. A geometric argument that shows us that this is the case. Okay? So, oh yeah, F net. This is net force, which is the sum of all the forces acting on the pendulum. Now, this is for an ideal pendulum. For a real pendulum, you still have this, but as you move faster and faster, you get more and more resistance from the air. So you have this uneven air resistance acting through the swing of the pendulum. Okay? And there are other forces. The flexing, the wave motion in this string, maybe some friction up here at the top. Or if you're holding it with your fingers wobble a little bit, and that introduces extra forces, right? So all those things confound the prediction here. But if you measure a real pendulum in this lab, the behavior is going to be very close to what this predicts. Okay? So I want you to understand this argument. I want you to understand this picture and how we put the similar triangles together. Okay? It's all very intuitive. You teach similar triangles to 12-year-olds. They have the conceptual, their brains developed enough to understand that. There's other things their brains aren't mature enough to do. But y'all are at the age where your brains are pretty mature. Okay? You don't have a lot more brain development going on. Yeah, your judgment's going to improve a little bit over the next several years. But as far as intellectual and ability to understand mathematics and physics, you're kind of at a peak. So they could take advantage of that. Okay, well, anyhow. The other thing we need to understand is that acceleration is just proportional to the net force. If you got twice as much net force, you have twice the acceleration. In other words, your velocity changes twice as quickly at twice the rate. Okay? So I want to talk about that a little bit. Then we'll talk about some of the consequences.